Well, we are now ready to start with our first organ system, looking at the cardiovascular system, and we now have 2 lectures worth of preparation under our belts. First lecture giving us what this organizing theme for this entire series being this dichotomy. If you are turning on the stress response because you're getting stressed like a normal mammal, you are doing something acute, energetic, explosive that's not going to last for too long, the stress response is wonderful, saves your life, highly adaptive. On the other hand, a central theme of this entire course is if you turn on the stress response too long, too often for purely psychological reasons, that's when you set yourself up for getting sick. So that was the main theme coming out of Lecture 1. Lecture 2 provided us with the tools, the toolbox of how you go about activating the stress response, which hormones you begin to secrete more of, epinephrine, glucocorticoids, some other ones, which hormones you secrete less of, growth hormone, there's reproductive sex hormones, and collectively, this is what powers your body to do that wonderfully adaptive stuff in the face of an acute stressor and all of that unhealthy disease-causing stuff in the face of chronic stress. So with that set here, now we can begin to apply those exact principles to the cardiovascular system. And in a lot of ways, if you wanted to pick the definitive, the iconic outpost of your body that gets done in by chronic stress, this is the one. Right off the bat, we know exactly how to apply the short-term logic. You are walking home from work, you're not quite paying attention, you come around a corner and, oh no, there's a lion there, and you have to go running for your life, and you better hope you turn on the cardiovascular stress response at that point. And it's actually very simple to do. If you don't worry about much in the way of details, you need to secrete glucocorticoids and epinephrine. You need to turn on the sympathetic nervous system, back one lecture, that SNS. And as we know from the previous lecture, if you were going to turn on the sympathetic, you were going to turn off the parasympathetic. So you've now got lots of epinephrine, lots of glucocorticoids in your bloodstream. Epinephrine directly increases cardiovascular activity. Glucocorticoids are interesting. They make it possible for epinephrine to work even more effectively. Really fancy biochemistry there. What they also do is they get up into your brain in very primitive brain stemmy areas and send messages to the neurons there, the neurons that send messages down to your heart. And suddenly, everything kicks into gear, everything is more activated, your heart rate goes up, your blood pressure goes up. Blood pressure, secondarily from the heart rate going, you are pumping the blood out more frequently. It comes bashing back with more force, pumped out again. The entire process is very adaptive because now you're delivering more blood, more glucose, more oxygen all over your body. But you don't want to deliver it all over your body. This is a crisis, and you're not saving your life by increasing blood flow to your ears. You're saving your life by sending it where it's needed. Thigh muscles, for example, which are going to save your life. Your lungs, which have to be breathing fast enough to supply the oxygen. The parts of the brain being stimulated by those glucocorticoids. The part of the brain that powers your heart, your lungs, all of that. Those are the ones that need more blood. Meanwhile, there's parts of your body that don't need the excess blood, where you decrease the blood flow. You divert it away from there. You divert it from your gut, from your reproductive organs, all of that, and this makes wonderful sense. And this was actually something that was first noted around 1833. This was a study by a bunch of physician scientists. And what it was, there was a man who had gotten some gunshot wound and apparently in his gut and had left a gaping hole there. And while the docs were about to fix him up there, they noticed something interesting, which was it was nice and red and rosy underneath with the blood flowing there, and they would get the guy angry about something, and it would suddenly get pale. It would blanch. It would be a much lighter color. You would decrease the blood flow to the intestines there. I mean, this is just sheer speculation, but maybe the guy was getting angry because, like, the damn doctors were sitting there, like, doing a science project on him instead of sewing him up. But this was some of the first evidence that stress will divert blood flow flow from an unessential area like the gut. That same logic from the first lecture: digest food, grow, reproduce, do all that stuff later. If there is a later, it's not essential right now. Deliver the blood where it's needed. So that's great. You've increased your heart rate. You've increased your blood pressure, your breathing rate. You're delivering the energy where it's needed. That's terrific. One additional thing you need to do, though. So you're that zebra. You've just gotten ripped to shreds by a lion, and you're bleeding like mad. And what do you want to do at that point? This may be a good point to try to get some more blood into your system. Try to decrease the amount of blood flowing out and try to replace it. How do you decrease the blood flowing out? One of the things you do at that point is you make a certain type of red blood cell, a platelet, a certain type of blood cell, and thanks to epinephrine, during a crisis, the platelets get stickier, they get gummier, more viscous, and what do? They facilitate forming a clot to stop the outflow of blood. So that's a great adaptation to decrease the amount of blood going out. But you got another problem here, which is you've lost a lot of the blood already. You want some replacement blood. How are you going to do that? Well, one solution is to make yourself some more blood cells, more red blood cells and white blood, and that's great. That's a great solution, but it's going to take you days or weeks to build those up again. So how else can you replace missing blood? Get some more water into your circulation. Increase your blood volume with more fluid. That'll make it easier to increase the blood pressure. Get some more fluid in there. So where are you going to get the fluid from? You're obviously, like in this physical crisis there, you're not going to suddenly get a lot more thirsty and drink a tureen of something. But where can you get water from? Your kidneys. What are your kidneys usually doing? They're sitting there, they're filtering water in, out of your circulation, salt balance, all sorts of stuff. And what you need to do is send a message down to the kidney saying, reabsorb some of that water. Don't turn it into urine. And what you secrete is a hormone from your pituitary called ADH, anti-diuretic hormone. A diuretic is something that makes you urinate. Tea, for example, is a diuretic. And an anti-diuretic hormone is something that makes you anti-diurese. It makes you stop urinating, and it causes your kidneys to retain more of the water. So that's great. That's terrific. Your blood pressure has gone up. Your heart rate has gone up. You're delivering it where it's needed. You're clotting blood if you're bleeding badly. And you've got this great mechanism here by which you reabsorb water out of the kidneys back into your circulation to maintain blood volume. Now, this makes wonderful sense, except this brings up one of these questions, a question which is so rarely aired in our public schools, part of the tragedy that is public education these days, so little discussed during educational sort of venues. This is this mystery of an enigma wrapped within a mystery, which is why is it if you're so stressed, sometimes you're going to pee in your pants? This doesn't make any sense. Because we've just seen the logic during the stress response is reabsorb water from the kidney, all of that. Why is it, though, that you have this paradoxical finding, nonetheless, that with the onset of severe stress, you lose control? And this is sufficiently the case that in many of the states where there are executions still, people are typically executed in diapers because you tend to wet your pants. Now, in order to appreciate the answer to this, we have to wrestle with the deep, abiding question of why do we have bladders? Now, bladder is kind of weird. The kidney is great. The kidney's wonderful. So we said you put water in, you take water out, you futz around with sodium. It's great. You could do it all day long. It's a great hobby. By the time stuff gets down to your kidneys and leaves your kidneys and then heads to your bladder is just this bladder thing. It doesn't do anything regulatory. It just stores stuff. By the time the urine goes south of your kidneys there, you can kiss it goodbye. You can't get it back from the bladder. It's just sitting there. Now, what's a bladder for in a lot of species? All sorts of species scent mark. What they do is individuals use their bladder, build up urine, and they go and they urinate around the periphery of their territory, and that gives all sorts of stay out of here, I mean it signals to anybody else smelling the urine. Scent marking is a very frequent use for urine in various species. That makes sense to have a bladder. However, we're not a scent-marking species. That's typically not what we do, although there's some interesting exceptions. I was actually reading recently when General George Patton was leading the troops into Germany during World War II, finally getting into Germany. Apparently, there was the point when they got to the Rhine River that Patton walked out to the middle of the bridge, and in front of his adoring, triumphant, cheering troops, he very ritualistically peed into the Rhine and announced, "I've been waiting a long time to do that." Actually, this seems to be a frequent theme in the military. I'm not quite sure why, but apparently also during the Korean War, very often you had American troops lined up on one side of the Yalu River, Chinese on the other, and apparently at this interface, this point of stalemate, the American troops would regularly line up and urinate into the Yalu River. Take that as they sent mark there. So despite these deeply moving historical circumstances of people urinating like hamsters, nonetheless, we still have this mystery. What's a bladder for? It's not clear. And the most important thing about it is it doesn't seem to be doing much. And here you have your classic acute physical crisis. You are running for your life. The lion's coming after you. And suddenly you got your choice. You could run for your life with or without 5 pounds of fluid sloshing around there on the bottom. You void your bladder. You get rid of the excess urine. So now we see exactly how the system works here. What's going on? Acute stressor, increased blood pressure, increased heart rate, retain the fluids there, clot, send it where it's needed, nowhere else. Makes wonderful sense for the short-term stress response. And now we barrel into our, by now, obligatory second half of this dichotomy. What happens when you do all of this too long because of chronic stress, especially chronic psychological stress? What you do is increase your blood pressure for 30 seconds, run away from the lion, you're saving your life. Increase your blood pressure chronically, and you are suffering from chronic hypertension, chronically elevated blood pressure. A little bit of the nuts and bolts first. How does that happen? So you have periods of the heart working really hard, pumping with more force, pumping more frequently. Blood pressure is increasing. It's going through the blood vessels with more force, distending the blood vessels out more from the sheer force of it. The blood vessels, in response, slowly begin to build up more muscle wrapping around them in response to this distension. They build up more muscle, which makes the blood vessels more rigid, which requires more force to get the blood through there. So you increase the blood pressure ever more, and we've got a vicious cycle here. So that's how you begin to get problems with hypertension. So what's the price that you pay? First off, at the level of your heart. What happens with heart function when you are chronically hypertensive? You get cardiologists and they're pretty impressed with the heart and would try to convince you of the same. Ultimately, a heart is just some big old mechanical pump like you could buy at Sears, and it has a lot of the same principles. If you make it work very hard, it begins to wear out after a while. And one version of the wearing out is if blood pressure is greatly increased, your heart muscle walls will pay for it. The heart pumps out the blood from one of its chambers, and the blood circulates around and comes back into a different chamber of the heart. And by definition, if it's being pumped out with a lot more force, it's going to slam back in there with more force and pound away on the wall there. And it happens to be, it's the left ventricle. That's the area that takes the brunt of returning blood under high force. And the muscle there begins to enlarge. You've got a hypertrophied left ventricle. And what is that sort of wobbly sort of extra muscle on that side? It begins to set the heart up for irregularities. So that's a problem. That's a first step there where you can get into trouble thanks to chronic hypertension. What about at the level of your blood vessels themselves? What could be happening there that gets you into trouble? And where you get your biggest problems has to do with a principle that runs through a lot of physiological systems in your circulatory system, your pulmonary system, a process called bifurcation. Okay, coming out of your heart, descending, for example, is one big, huge blood vessel called the descending aorta. Don't worry about the name of it. One big, huge blood vessel, which after a certain distance splits into two. bifurcates into two. And after a while, those two smaller vessels, each one of those is going to split into two, bifurcate, bifurcate, bifurcate endlessly until you've bifurcated your way down into little capillaries. What the circulatory system is about is a whole bunch of these bifurcations. So what's one of the things that happens when you increase blood pressure? The bifurcation, the point right where it divides, that's the point of the wall of the blood vessel that is splitting this river of blood and splitting it in two. Or another way of stating it is, that's the part of your blood vessel that's getting pounded with the most force there. So you increase blood pressure, and you begin to have a problem that's straight out of 9th grade physics, and it describes all sorts of fluids moving through any sort of tube. This is why your bathroom plumbing wears out after a while. By definition, if you've got a tube and you got fluid moving through it, and it moves through with more force, you've increased your blood pressure, move it through with more force, and you eventually begin to get fluid turbulence and little eddies and little tsunamis of blood there. And as you begin to get the turbulence, what it does is it slams into the walls of the blood vessels with more force. And again, particularly taking the brunt of it are those points of bifurcation. So enough of that slamming against the walls of the blood vessels, and you begin to get little bits of damage there, little bits of tearing, little bits of scarring, little bit of spots there that wind up getting inflamed. And that turns out to be a critical process there, one that's appreciated more and more in cardiology. You begin to get little bits of inflammation around these spots of vessel damage. Inflammation, there's all sorts of inflammatory cells that wind up getting in there, start sticking to there, and suddenly it's beginning to glom things up there a bit. You're beginning to get a bit of a plaque. Why does that get you in trouble? For lots of reasons now. Now along comes fat and glucose and cholesterol, and that stuff is more likely to stick onto this inflamed little plaque. Where's the fat and glucose and cholesterol coming from? That's exactly the stuff you're mobilizing out of storage sites to feed your exercising muscle. So you get this double whammy here between the metabolic stress response and the cardiovascular one. Now, this whole business about inflammation has really come to the forefront in the field. 20 years ago, if you could only measure one thing in the bloodstream and you wanted to get a sense about how somebody's cardiovascular system was doing, what would you measure? You would measure somebody's cholesterol levels. That was the number everybody got obsessed over. That was the number you would use as a pickup line at parties, bragging about how low your cholesterol. That was just the defining point of the field. And in recent years, people have realized more and more, your amount of cholesterol is important, but something else is more important. In other words, you can have just cholesterol coming out the wazoo. You could be eating 3 dozen eggs a day, and if you had absolutely unblemished healthy blood vessel walls, the cholesterol really doesn't have much to stick to. It's not until you begin to get inflammation, inflammatory damage there, that the cholesterol has a spot that is going to home in on. The inflammation appears to be the starting step. And it's for that reason that there's been this transition in the field from we can only measure one thing, measuring cholesterol, over to measuring one thing, something called CRP, C-reactive protein, which is a marker of the amount of inflammation. So that's a problem. But you can set yourself up for a second problem here. And this is one that's been shown in a lot of experimental settings. Okay, you have hypertension, and that could set you up for damage to your blood vessels. Very interesting research, very clear-cut research done with non-human primates showing that if you couple hypertension with a high-fat diet, you get far more vascular damage than either alone. And this turns out to make perfect sense. One reason is obvious. You get more fat, and we've just heard if you've got inflamed, damaged blood vessels, more fat there is going to be more likely to glom on and cause an atherosclerotic plaque and plug up your blood vessels. As we're going to hear in a subsequent lecture, people are just realizing there's a really interesting, unexpected additional reason, which is you have a high-fat diet, and you're going to get more fat stored in your body. And something that just knocked fatologists on their rear as this became clear is fat cells are able to secrete certain inflammatory messengers. totally interesting, unexpected. What's our implication here? A high-fat diet is always also going to increase the amount of these inflammatory signals coming out of your fat cells. So look now, when you have a high-fat diet, whatever damage there is to the blood vessels, they're more likely to get inflammatory plaques forming, and the elevated fat, glucose, cholesterol is more likely to stick onto. You're going to get more atherosclerotic disease. And what that sets you up for are a number of different types of potential disasters. You block the blood vessel here entirely, or it's partially blocked and you get enough blood force, enough shearing force, that eventually you knock this little plaque loose. You get what's called a thrombus, and that could get you into real trouble now. If it goes wandering up into one of your heart vessels, coronary heart vessels, and clogs things there, you might have a heart attack. If it gets into a vessel in the brain, you have a stroke. Not good. Now, what this brings us to is this third outpost of what can go wrong. We've now seen how chronic hypertension, how chronic stress-induced hypertension can be bad news for your heart muscles, can be bad news for your blood vessels. Now to focus in on a particular type of blood vessel, one I just alluded to, the blood vessels bringing blood to your heart, your coronary blood vessels. Now, when you think about it, at first, this actually doesn't make any sense at all. Wait a second, your heart, which is just swimming around in oceans of blood, your heart has to have specialized blood vessels feeding it blood. When it's the heart, what it does is it's in contact with blood. This initially makes no sense, but think about, you work in the building that regulates water flow through some reservoir, town reservoir, and you work 15 feet away from the reservoir, and you're thirsty. If you're thirsty, you don't go out to the reservoir with a bucket and drop it down in there and pull some water out of there to sip the rest of the day. What do? You do what you do anywhere else in the city. You go to a water fountain that's in there in the building. It is exactly equivalent to what happens in the heart. Heart muscle can't feed itself from these oceans of blood blasting in and out, so you have coronary blood vessels. And it turns out coronary blood vessels are not vessels you want to damage from chronic hypertension. Normally, there's something really helpful that coronary blood vessels do when they're perfectly healthy. Along comes the lion, you're running for your life, it's a crisis, you need more blood delivered to your heart because your heart's working so hard, and in a healthy coronary blood vessel, something terrific happens there. They vasodilate. They increase, they become looser, so even more blood can go blasting through there and bring energy, and your heart could keep up with demands. That's great. Begin to damage those coronary blood vessels, that inflammatory plaque stuff, and something so insidious, so unfair happens at that point in terms of how things can go so wrong. What begins to happen is, once those coronary vessels are damaged, when you increase blood flow during a period of stress, these vessels no longer vasodilate, they constrict. They constrict, and exactly when your heart needs a ton of blood, there's less of it coming through. And this is not a good thing. How does this work? It turns out there's some chemicals that are released from the coronary blood vessels when the heart's working hard that vasodilate, a bunch of these. Interestingly, one of those chemicals is related to nitric oxide. So they normally work there, but begin to get damaged coronary blood vessels with plaques and stuff, and this nice, helpful vasodilatory signals are unable to get out there. So you're totally up the creek now. You've got damaged coronary blood vessels, and exactly when your heart needs more energy during a major stressor, that's exactly when these blood vessels stab you in the heart by constricting even more. And your heart, thus, does not get enough blood flow. It doesn't get enough oxygen. It doesn't get enough glucose. It doesn't get enough energy. And you have cardiac ischemia, myocardial ischemia. Your heart muscles are not getting enough of the stuff they need. Now, studying that was traditionally kind of hard to do because the only way you could see if somebody had this problem with cardiac ischemia would be to put them in this very artificial setting, take them into the doctor's office and make them run to the point of exhaustion on a treadmill when you've got all the electrodes stuck up with them. And you could get information, but this admittedly is a very artificial setting. Not a lot of people who are potentially having emerging heart disease are having problems with it because they are running up dozens of flights of stairs nonstop and then seeing what their blood pressure was like. Instead, the problems pop up throughout the day. So the question became, What's happening to function of coronary vessels throughout the day? When you begin to have vessels that are damaged, who knows? You can't measure it. And then some years back, somebody came up with the wonderful technology where you can measure it. You could do what's called ambulatory cardiology, where you have these little devices that are monitored, and it could monitor what's going on with your heart throughout the day. And back came a surprise, which is people who begin to have damaged coronary blood vessels, they're having those little ischemic insults to their heart muscles just all the time throughout the day. This is not the realm of massive, sudden physical stressor and that history of stress-induced damage to your blood vessels. You begin to pay for it then. It was shocking to everyone how often you get little problems with that, and how often then the heart muscle is not getting enough energy and it hurts. Angina is the term for it. So we've seen here ways in which you can get into trouble by too much sympathetic arousal with chronic stress, damaging your heart muscles, damaging vessels throughout your body, damaging the coronary blood vessels. All of that conceptually due to too much of a let's kick into action signal coming, too much sympathetic nervous system. There's a flip side to it as well, which is you can also get into trouble if you have too little of the inhibitory signal coming in there, too little of parasympathetic tone. You remember sympathetic, emergency arousal, parasympathetic, calm, vegetative, activate the parasympathetic nervous system, and your heart's going to slow down by way of something called the vagus nerve. So you can get into trouble either by too much sympathetic screaming at your heart or too little vagal calming, or if you're really in for trouble, both of them are going wrong, and this is another way you can have problems there. Interesting way you could pick up on that, showing just how delicate this whole system is. Inhale, take a breath in, and you slightly stimulate your sympathetic nervous system, and your heart rate increases a little bit. Exhale, and you stimulate parasympathetic, and things slow down a little bit. So if the system is working wonderfully, every time you inhale, you get a little sympathetic hiccup, exhale, parasympathetic, and you look at the pattern of beats, they're a little bit longer, a little shorter, a little bit longer. They're quite variable. Begin to have a damaged parasympathetic nervous system. If stress has been driving it to the point where it really doesn't do what it's supposed to do, you inhale, and your heart rate speeds up a little bit. You exhale, and because the parasympathetic nervous system has been driven into coma, you don't get as much of a slowing down. What does that look like? You look at somebody's heart rate pattern, and there's not as much of that variability. That's a very hot subject these days for picking up problems with parasympathetic nervous system. Okay, so all of these are scenarios where chronic stress will chronically pound away at your blood vessels, your heart, all of that, and all of that can potentially culminate into one of the great crises, which is sudden cardiac death. And we all know the dramatic version of it. Guy gets terrible news and he's wailing, and suddenly he clutches his chest and keels over dead, and sudden cardiac arrest. And for the most part, this is a movie plot. This is very rare. Nonetheless, it pops up in all sorts of settings. One example, during the 1991 Gulf War, there were attacks from Iraq, Scud missiles onto Israel, and the number of people killed by missiles were considerably smaller than the number of people who had heart attacks during the period of the missile strikes. Sudden cardiac arrest. Massive increase in cardiac demand. You're running away from a lion. You're running a marathon. You are just euphoric and hyperactive and agitated because you've just taken some guy's pawn in this chess game. Whatever it is, you can push things to a point where down you go. It is too extreme. And this brings up a final really interesting point, which is, what about when you get people who have heart attacks, even sudden cardiac death, not because a lion is chasing them, but because they're in the middle of something wildly pleasurable? The archetypal example, of course, being the person who has a fatal heart attack right in the middle of sex. What is that about? We're talking about stress here. What's this going on? And what this brings in here is the possibility of something such as fatal pleasure. And it makes perfect sense. If you are leaping up with joy or leaping up with terror or leaping up with rage, you're leaping up. It's taking muscular work. your heart's having to work harder. And when you look closely at what the heart's up to, when there's an activated state, you cannot tell whether this is someone who is just about to commit a murder or someone who is just about to have an orgasm.